Hey AP, in this video we're going to talk about gases and kinetic molecular theory. For a lot of what we're going to talk about today is review from what we've talked about in chemistry last year, the year before. So we're not going to go through a bunch of examples, we're just going to talk about logistics of most of these things. We're finally going to get into some math, so some of you are very excited about that opportunity. And then we'll go through a couple of the newer relationships and formulas that we'll use moving forward. So as we know, pressure is when I feel like my camera's big, but it's not. Pressure is when gas particles collide with the walls of the container. So that is pressure. It's really the collisions of the gas molecules with the container. And we have our pressure units. We have our units of, that should say 760. 1 atmosphere, which is equal to 760 millimeters of mercury. Millimeters of mercury and torr are the same thing. They're just different units. And then we also have kilopascals, so it equals 101.3 kilopascals. Those conversions are also found on your reference sheet here. So we're focusing on gases, liquids, and solutions. So a lot of what we're going to use in this unit moving forward is here. But here we have our gas constant, which we'll get to, and then here's our pressure units. 1 atmosphere, 760 millimeters mercury, 760 torr. AP doesn't use kilopascals very much. There's still some worksheets we'll find that has them, so that's why I put it on our notes, but we might not use it very much at all. So kinetic molecular theory, you guys looked at a POGL back in chemistry on this, and we put it down into just really 3 pieces, but now we're expanding upon it. So first off, a gas is made up of tiny particles whose size is insignificant compared to the space between them. So we're saying a gas particle is so tiny, we pretend it doesn't have a volume because the space between one gas particle and another gas particle is so big that it really doesn't matter. Really don't take up space. We say that they move randomly in straight lines at various speeds, so they don't cruise around, they go straight around. And that they're at various speeds. And we'll look really more at this tomorrow when we look at Maxwell-Boltzmann distributions. Then forces of attraction and repulsion between 2 particles are insignificant. In other words, 2 particles are not attracted to each other, nor do they repel each other. Then colliding particles have elastic collisions. And when they collide with the walls of the container, that creates the pressure. An elastic collision means that when 2 of them collide, they just bounce right off each other in the opposite direction they came from. They don't stick. They don't then hover around each other. They just bloop and go away. And then same thing happens with the size of the container, just bounces off and goes about its way. Finally, the average kinetic energy of a gas particle is proportional to the Kelvin temperature. So this is why we have to use Kelvin. Okay, that's because at 0 Kelvin, we say the molecules stop moving. There is some research that says that this might not be perfectly true, but it hasn't been studied fully yet. So we just stick with 0 Kelvin means they stop moving. All right, on to some math. Gas law calculations. We obviously have to start with our basics of our basic gas laws. And in this chart, we have the laws' names. You won't have to memorize the names of the laws. However, you might get said like using Boyle's law, which is this, So it's good to just have a reference of the 2 of them. So we have our formula. Remember, P1V1 equals P2V2. We have our initial conditions and our final conditions. When we have this formula, these are inversely proportional. And so if I were to graph that, inversely means when one's low, the other one's high. So at low volumes, I have high pressure. At high volumes, I have low pressure, and it looks like this. Okay. Charles' law looks at the relationship between volume and temperature, and again here, temperature has to be in Kelvin. In terms of pressure units up here, they just have to match, and same with volume, so it could be milliliters or liters. Here for Charles' law, when we have V1 over T1 equals V2 over T2, this is directly proportional. And that means that at low temperatures, we have low volume. And at high temperatures, we have high volume. So it makes a direct relationship like so. And this makes sense because low temperatures, molecules aren't moving around very much. Therefore, they're fairly close together. They haven't spread out so far, so they're taking up less space. Because I'm keeping pressure constant, as they start to expand and take up more space, they're going to collide with the container. We don't want more collisions. We want pressure to stay constant, so my container expands. And that's why we get the bigger volume. Gay-Lussac's law looks at the relationship between pressure and temperature. Again, temperature needs to be in Kelvin because it's based on the kinetic energy. Again, this is directly proportional, so the graph is going to look the same. And this also makes sense. If volume has to stay constant, so my container here, and I'm increasing the temperature, means that I'm increasing the kinetic energy of my molecules. They're moving faster. If my volume cannot expand, it's going to stay here. As they move faster, then they're going to collide with the sides of the container more. As they collide with the sides of the container more, we have more pressure, more collisions. Avogadro's law is not one that we've talked a ton about before, but it does introduce the idea of moles and volume and their relationship. Similarly to Charles and Gay-Lussac's law, it's a direct relationship, which also makes sense. As I increase the number of moles, I'm going to increase the volume that I have in my container if I am keeping pressure constant. So again, if I start with a small container and I start to increase my moles of gas, so I'm putting in more particles. Well, if my pressure needs to stay constant, number of collisions needs to stay constant, and I'm increasing the number inside, that needs to get bigger and expand to accommodate for more collisions that are happening. So that way they end up with the same number of collisions on the outside of the container, even though I have way more particles inside. Finally, I can combine all four of these together into the combined gas law. And that we would use if we're changing things like pressure, volume, and moles of gas and temperature. So all four variables changing from one conditions to the next conditions. And we don't have to worry about our relationships there. All right, further on to review, we have our ideal gas law, which is PIV-NERT. Okay, here, most gases only obey this law at temperatures and pressures that are at or above standard temperature and pressure. Remember that STP, which is also in your green sheets, is 0 degrees Celsius. Remember that is 273 Kelvin and 1 atmosphere. So standard equation for ideal gas law, PV equals nRT, PIV-NERT. Okay. Remember that P is pressure, V is volume. This time it has to be in liters because of our R value. N is moles, T is temperature in Kelvin. Like I said, R is that gas law constant. Luckily for you, you don't have to memorize them. They're on your sheet. So we can see them here. We've got R and we have 3 different values listed. This first value we're going to come back to in a little bit. It doesn't have units that we can use right now. The other 2 are ones that we're going to use. And notice that the difference in our units is the pressure units, atmospheres and torr. So in order to determine which R value I need to use, they need to match my units of pressure. So you might have to do some conversions, or you just choose the respective R value. Now, what we can start to do with our ideal gas law is look at things like molar mass, so calculate molar mass of a gas, and we can calculate density of a gas using the information in our ideal gas law. You could also rearrange your equation to include molar mass. Remember that molar mass, which we're going to abbreviate as capital M, is, molar mass is grams per mole. Okay, so that means that if I have molar mass, I'm going to need to have grams in there, and molar mass divided by that. So we end up with moles, which is what I want. So I'm substituting that in for N. Okay, so I have this equation here that includes my molar mass. And what I can also include, because I'm going to have mass and volume. So if I move volume over, I'd have mass divided by volume. We know that density is mass per volume, usually grams per milliliter or grams per liter, which is what we'll have here. I can have density in my equation. So what I can further do is I can really rearrange my ideal gas law into molar mass equals dirt, DRT, over P. So molar mass is dirty P. This equation not on your reference guide. It's just one that you're going to need to know if you're asked to do it. Now, you could go through a couple of steps with your ideal gas law. You could solve for volume. Once you have molar mass, you can then convert based on the mass you have to get to grams, and then take grams divided by volume to get density. So you don't have to use this formula at all. I usually don't, because it's just not one that I remember. I just get my information from here, do a couple extra calculations, and we'll practice that in class as well. Piv Nert, though, is on your green sheet right at the top here. And the rest of these we'll talk about in a minute. All right, on to some more. So a couple newer ones. Some of you, depending upon when you had chem last year or the year before, may or may not have seen Dalton's law of partial pressures. Just kind of depends how the year was going. So with that, we said that the total pressure inside of a container is equal to the pressure of the sums of the individual gases. So sum of individual gas pressures equal to the total pressure. So my total pressure is equal to my individual pressures. So if I have hydrogen and oxygen and nitrogen inside a container, pressures of each one of them adds up to equal the total pressure. And that makes sense because I'm adding more things into my container, more collisions, so collisions from each one of those get added up to be my total collisions, which is my total pressure. Important to note that these need to have the same units of pressure on all of these in order to add them. And that makes sense. Now we can do further calculations here. And if I know my total pressure, I can also know something about my total number of moles of gas. Okay, so maybe we don't know about my individual pressures, but I know the total moles of gas that I have in my container. Then I can use this, which looks just a derivation of my ideal gas law. I can use this to calculate my total pressure if I know my total number of moles is also total pressure. So just a note there that you can figure this out if you know your moles are T and V, or you might be given partial pressures and asked to find the total. Okay. Next, we have root mean square speed. And we abbreviate this with URMS, root mean squared. This is the velocity of our gas particles. And it's calculated by taking the square root of 3 times RT divided by M. And remember, M is molar mass. This, because we're looking at speeds and velocity, means that we need to use that other R value, the one that we haven't seen before. That R value is 8.314, and it shows up on your sheet as joules per mole Kelvin. However, if you start dissecting joules, you will get kilograms meter squared per second squared, and this is where these velocity units start to come in. Okay. Again, temperature, as always, has to be in Kelvin. And in this, your molar mass, to combat the molar mass here, kilograms per moles, is supposed to be in kilograms per mole and not grams per mole like we're used to. However, because this is a relative velocity, right? We're just comparing two things together to see which one's faster. We don't have to convert it back into kilograms. We can leave it into grams because we're just comparing two things of grams. We're not saying, oh, this is this velocity. We're saying like, of these two, which one goes faster? So that works to our favor. So let's do an example of this because this one is brand new. So for this one, it asks us to determine the URMS, so the root mean square speed of helium at 25 degrees Celsius and 50 degrees Celsius. Remember, first, they have to be in Kelvin. And I need my calculator. So 25 Celsius plus 273 is 298 Kelvin. And here is 323 Kelvin. So you all can see. So URMS of my first one, 3 times R, 8.314, times my temperature, 298 Kelvin, divided by my molar mass. My molar mass of helium is, and we're just looking at relatives, so we can pull it right off the periodic table, 4. 4. So we need to take the square root, make this brighter so y'all can see. So square root of 3 times 8 is 298 divided by, and it's all multiplying and dividing, so I don't need extra parentheses, 4 equals, and I get 43.1, and I'm going to go off sig figs off my measured number, which is my 25 degrees Celsius. My other one, 50 degrees Celsius, 8.314, 323, 4. So the only thing that changes is my temperature. So I'm going to be lazy and just re-enter it and then change this to 323. And it goes up 44.9. All right. Then you ask yourself, does that make sense? And we would say, well, yeah, it does make sense, because if I'm at a higher temperature, temperature is directly proportional to kinetic energy. Higher temperature, higher kinetic energy. Higher kinetic energy means they move faster. So if they move faster, they're going to have a higher root mean squared. So temperature, we know that as we increase temperature, we will increase our URMS. Okay. Let's think about something else. Well, what about molar mass? Okay. So let's just pick a molecule that has a molar mass bigger than 4. So for example, we could do neon. Neon has a molar mass of 20.18. And let's say that it's also at 50 degrees Celsius. Well, instead of it being divided by 4, it's being divided by 20.18. Not 420, just 20. Okay. So we also know that if we divide by a bigger number, it's going to make it smaller. But just to be sure, here we go, 19.9. So I have cut my number in half by going from 4 to 20. So that means that bigger molecules move slower. Also makes sense, right? Small ones zip around and move fast, like a little race car. Big ones, like a semi-truck, take a little bit to get going. So molar mass, as I increase my molar mass, I decrease my root mean square speed. Also makes sense. Most of the time, you're just going to be given questions. You won't have to do a lot of these calculations. And this formula doesn't show up on your formula sheet. So it means more than likely you won't be asked to do a calculation with it. So you'll probably have to answer questions about this, like 2 molecules, this one and this one, which one's going to have the faster root mean square velocity? And you'd say, well, this one, because it has the smaller molar mass, or this one, because that's the higher temperature. All right, 2 more laws, and then we're done. Keep hanging in there. So we've got Graham's law of effusion and diffusion, and we need to know what those terms mean. They're similar but different. So if I'm effusing, so effusion is a process where gases escapes from one vessel to another by passing through a small, read tiny, opening. Okay, so it goes from one area to another. So this is things like when a balloon deflates because the air molecules are escaping through the individual molecules of latex in the balloon, right? It just seems to just like shrink on its own. Okay, so that's effusion. Diffusion is a process where a homogeneous mixture is formed by random mixing of 2 different gases. So I have 2 containers, 2 bulbs of gas, and I have a barrier between the 2 of them, and I open that barrier and I allow the 2 gases to mix together. That is diffusion. Also happens, you have diffusers, and that would be like, usually see them in bathrooms a lot of the time, and where that scent leaves the solid that it's in, and then it escapes and comes out into the room, and then you can smell it. That's it mixing with the air. So that's also diffusion. It's also how you can smell popcorn in the next room across the hall, right? Because those smelly particles of the popcorn are drifting through the air and they reach your nose. So that's diffusion. whereas effusion is where it gets through an opening. So we have, similar to root mean squared, we also have rates to calculate which gas molecules move faster. And just like before, that's based off of size, molar mass, and also density, right? A more dense gas is going to move slower than a lesser dense gas. And we can see that here by looking at our rate of the two is proportional to the inverse of the square root of its density or the square root of its molar mass. And we can see that smaller gas particles are going to effuse and diffuse faster. We'll do a couple calculations here. But again, similar to up here, you're probably going to be asked, here are two molecules or two gases, which one diffuses faster? Well, the one that's smaller in terms of its molar mass or the one that's less dense. Finally, we have Henry's law. Henry's law looks at the relationship between temperature and solubility of gases. So we can think about soda and its carbonation. And we know that as we increase the temperature of our soda, it stays less carbonated because my gas molecules jump out of the solution. They don't like to stay dissolved. And we can say that gas solubility, or the solubility of gas in other things, decreases with an increase in temperature. And this makes sense because as the temperature increases, particles have more energy, because remember it's proportional to its kinetic energy, and therefore they can escape from the solvent. So this is why fish tanks should be, they're warm, but they're not hot, right? And that's because we need the air, the gas molecules that you are bubbling in, you want them to stay. You want the oxygen to stay in there. If it got too hot, most of the oxygen would leave and your fish would suffocate, which would be bad. So on that note, you have finished your gas laws, and we'll start to practice lots and lots and lots of math. And we'll look at those Maxwell-Boltzmann equations as well in terms of velocities of gas particles. So good job.